Let's learn how to use the Arrhenius equation. Here we have the Arrhenius equation. You can see that K is the rate constant. We learned about the rate constant when we did the rate law. A is the frequency factor. EA is the activation energy. R is 8.314 joule per mole K. And what do you think T stands for? Yes, temperature. And since the units of R are joule per mole K, then temperature must be expressed in, what do you think? Correct, Kelvin. So when we were talking about the rate law, and let me quickly jot down the rate law of some fictitious reaction, we had the rate constant. And when we determined the rate constant, we said, when we determined the rate law, it was determined experimentally. So we monitored the reaction, calculated the rate, and then determined the rate law. And the rate constant was determined afterwards. All the experiments were done at the same temperature so that K would be constant. So K is temperature dependent. If we increase the temperature, don't you think rate increases? Because the particles are now moving about faster and colliding with each other more frequently. So if the temperature increases and rate increases, that must mean that K must increase because the concentration would stay the same. That's unchanged. So increase K, increase rate, or increase rate, increase K. So here we have the rate constant, and now we're looking at the effective temperature on reaction rate. So T, temperature, is in the denominator. So if we increase this denominator, making the denominator bigger, this entire value gets smaller, and then we have a negative exponent. So this entire value gets bigger and K gets bigger. Let's take the natural log of both sides. Remember that when numbers are that a natural log is an exponent, a log is an exponent, and when we multiply numbers together, we add the exponent. So that leaves us with natural log of A plus natural log E to the minus EA over RT. Here we have inverses of each other. That leaves us with, I'm just going to rearrange this a little bit over here. Putting EA over RT, starting with that. And T is in the denominator. I'm factoring that out like this. And now you can see that we have something that looks like an equation of a straight line, y equals mx plus b. So x on the x-axis would be 1 over the Kelvin temperature, and the slope is negative EA over R. If we were to graph many values, we would have natural log of K on the y-axis, 1 over T, and that would be in reciprocal kelvins. Right here you have the y-intercept, and the slope would equal negative EA over R. So if you wanted to get EA, don't forget to rearrange. EA would equal negative the slope times R, so that you get a positive activation energy. Problem, we write the Arrhenius equation twice, one for K2 and one for K1. And now I want to combine these two by subtraction. So natural log K2 subtract natural log of K1 equals this portion right here, subtract this portion. So you can see that the natural log of A, subtract natural log of A, that's going to cancel out. And we're going to factor out negative EA over R. And of course, when these are exponents and when we subtract exponents, that means we're dividing numbers. Different forms of this is called the 2-point form of the Arrhenius equation because we have 2 points, 2 Ks, and 2 temperatures. I just factor out the negative EA, so I have 2 over 1 and 2 T2 minus T1. You'll see other forms of the Arrhenius equation where the negative is distributed through, and so this actually, they distribute this through. This becomes positive, so it's T1 minus T2, but this is how I write it. Both are mathematically correct. Choose your favorite version. So now we have an equation that we can use, and we're going to plug in some values. And we're asked to convert this into kilojoules, so we'll divide by 1,000. Now, one of the things you could have done, instead of using 8.314 joule per mole K, you could have written it as 8.314 times 10 to the minus third kilojoule per mole K, and then you would have had your answer directly in kilojoules. It might not seem obvious, but when we subtract this by this, we're actually left with, when you do the subtraction, only 2 significant figures. So this really should be 1.5 times 10 to the third kilojoule per mole. 1.5 times 10 to the third kilojoule per mole. Let me show you what I mean about this right here. If I had written this, maybe I did it in a different color, with 8.314 times 10 to the minus 3, this is a little sloppy here. Let me